Let's start with our second chapter lesson here, looking at how to use curved arrows in illustrating reactions. So again, this is kind of review from an earlier lesson, so I'm going to try to hurry through this and just emphasize those things that we'll need to carry forward. We know that we use a curved arrow so that it points from the source of an electron, from a curved arrow, showing an electron transfer. So when we think of curved arrows, it goes from an electron rich to an electron deficient or electron poor arrow. Electrons can form bonds, or electrons will collapse back onto atoms. And we're always going to flow the electrons from a sense of higher density to the side of lower density. Never use a curved arrow to show the movement of atoms. We know that's illegal. And make sure the movement of electrons shown by the curved arrow does not violate the octet rule for the elements in the second row of the periodic table. By other words, they cannot expand the octet because the second row, as well as the first, hydrogen, helium, simply don't have d orbitals available. To remind ourselves, the origin of the electron arrow is from the electron rich. We think about hydrogen hooked to oxygen. The electron-rich area of oxygen is the origin of the arrow, and it goes towards the electron-deficient hydrogen ion. The new bond forms from a pair of electrons reaching over to grab the proton. The resulting molecule has two sets of electron dots remaining, where that third set now forms the new bond. Never start from positive and go back to the negative. Here we see an example of ammonia, a very rich electron area on the top of the nitrogen. You can see that it's a very polar molecule, a site of electrons. And we have a very polar region here in this functional group called a carbonyl. Remember also that the electrons have dots that are not drawn, but we know that are there. Carbonyl, as the electron density is being pulled from the carbon up to the oxygen, creates this partially positive target for the electrons. So I can see a new bond forming right here, showing that, and again, another bond up here, where in a set of electrons that were a bond collapsed up on top of the oxygen. So now I have three sets of lone pairs up here, and the new bond connecting the original electrons here. And remember, this is just a formal charge on nitrogen of +1. The moral of this story is always start at the negative and point towards the positive as we move electrons around. Electron rich to a positive hydrogen. The bond collapses and places the dots on the oxygen. Again, even though they're not drawn, we know that they're there. So electron rich to electron deficient. So section 3.2 just simply reminds us of the rules then for establishing electron flow. We're going to introduce then a third, well, I say third because in chemistry we had the Arrhenius definition of acids and bases, the Bronsted-Lowry definition of acids and bases, and we're going to kind of get our feet wet with our third section, Lewis, acids and bases, by far the most helpful in organic chemistry. Electron deficient atoms. I'm going to need to pause and let the dog out. Okay, thank you. Any electron deficient atom can act as a Lewis acid. Electron deficient Lewis acid. And many compounds that contain group 3A elements, and what does that mean? That could be boron and aluminum are group 3A. They're very electron deficient, and they make very good Lewis acids. I need to define Lewis acids, and we will in a moment, but they are electron pair acceptors. And I'm going to stress that in a moment. Other compounds that have atoms with vacant orbitals also act as Lewis acids, such as the zinc ion and the iron Roman numeral 3 ions. Lewis acids, electron pair acceptors. I'll dwell on that definitely coming up more, but I'm just giving you the inkling of what that means. All right, let's share a little bit of what this is showing. I have an acid-base chemistry going on here, and I want to just kind of share with you step by step of what I see. I have a molecular bromine, Br2, drawn out with a single bond and its valence electron shown around. And I'm reacting that with iron 3 bromide, which is an ionic compound, FeBr3. Now, notice that bromine to bromine has a single covalent bond, and iron 3 bromide has an electron deficient iron. What I mean for that is it does not have a complete octet. It only has 3 bonds instead of 4, giving it an octet. A Lewis acid is electron deficient. It will accept a pair of electrons. Electron pair, I should write acceptor. The BR has all kinds of electron pairs around it. Anything that can donate an electron pair is referred to as a Lewis base. I'll emphasize in the next slide as well, we're getting our feet wet for the first time with the Lewis theory of acid-base chemistry. In Lewis theory, we do not transfer protons. That's Bronsted-Lowry. This is a new format where we're hooking together an acid base using curved arrows to show electron movement. Notice that a pair of electrons on the bromine attached or hooked onto, bonded with the iron that was electron deficient. So now all of a sudden on this side, where I call it the product side, we have one product, not conjugate pairs like the Bronsted-Lowry, but one single product. And notice that the new bond forms, and that's giving bromine a formal charge of +1, and it completed the octet of iron Roman numeral 3, giving it a -1 formal charge. But one product formed through the transfer of a pair of electrons. The base transfers an electron, the acid accepts the electron and forms a bond, making a single product. The elements that make good acids, well, boron, because it's also in group 3A, it has only 3 spots, it's electron deficient. It has an open spot for this electron pair to come seeking to bond there. Same with aluminum. It has 3 valence electrons. It has an open spot, a site of attachment for a pair of electrons. Zinc ion, same thing. Iron ion, same thing. They have electron deficient octets, making them good targets for electron pairs to fill those vacant orbitals. Let's practice using curved arrows to follow the reaction steps. We're just practicing curved arrows. What we want to do is just take a good look from the left to the right side and see what's changed. I notice here on the OH is a very rich electron area. And over here I see on the product side that it's attached a new hydrogen to it. Remember, this is a very polar bond for HCl. I have an electron-rich area on the OH negative, and I have an electron-deficient or electron-poor area on the hydrogen ion. My first curved arrow will originate at a pair of electrons and point to the hydrogen ion, electron-rich to electron-poor. And that becomes the new bond you see on the product side. The electrons that were originally lone pair are now involved in a bond. The +1 results in the formal charge developed on oxygen. What about these 2 electrons that were originally in a bond. They're going to collapse back onto the atom of chloride, and now I can see all 8 dots are on the chloride ion. Its formal charge of -1. We have 2 electron arrows needed as A goes to B. Now remember the topic of our chapter, acids and bases. This is a Bronsted-Lowry acid-base reactions because I can see conjugate pairs. We had a base form a conjugate acid, and we have an acid form its conjugate base. We had a proton transferred. Let's take a look here. We have oxygen. We have on the reactant side, I'm noticing we have an oxygen that's electron rich, and over here on the product side, I notice that it's developed a negative charge. I see an electron-rich area on the nitrogen, and I notice over here on the product side, it's attached to another hydrogen. Where does that hydrogen come from? I think when I erased this, if I did, I might have erased the H. Yep, I sure did. There it is. So when I created this slide, there was an H here. Could you please add that? Because right now there is no H for the nitrogen to go get. And when I was erasing, I probably took it with. Because I need to start at the electron pair of the nitrogen, and I want to go to the electron poor hydrogen ion. When it does so, we form the new product with the nitrogen, and those original dots, these dots right here, are now a bond. Don't forget the formal charge that's developed on the N+. This bond is 2 electrons. Where did they go? Well, they collapsed back in onto the oxygen, and now you see 3 sets of dots on the O and its -1 formal charge. I just needed to make sure that H randomly just didn't appear. It came from somewhere. I needed to draw that back on, my mistake in the original drawing. So when I present this in class, I'm going to make sure to add that hydrogen there. Here's one from your sapling. And again, as soon as I see conjugate pairs, I know it's Bronsted-Lowry. I know that OH and water differ by 1 hydrogen ion. I notice that OH and O negative differ by 1 hydrogen ion. This is that functional group known as the carboxylic acid. COOH is cool. So let's take a peek at what's happened. We have an electron-rich area on the oxygen abstracting the proton from the carboxylic acid. These electron dots now become a bond to form a water molecule. These electrons that were originally in a bond collapse back onto the oxygen, creating 3 sets of dots and a -1 charge to represent its formal charge. 2 sets of arrows for this particular Bronsted-Lowry reaction. An acid formed its conjugate base. The base formed its conjugate acid. We have pairs of products, so I know it's a Bronsted-Lowry acid-base reaction. We can try one more. As soon as I see nitrogen, I automatically know it's a base. Nitrogen has this lone pair, and it will form its conjugate acid. The nitrogen will pull the proton. Based on the electronegativity difference, that hydrogen is very positive, and we can see these electrons that were a lone pair are now a bond. These electrons that were a bond collapse back onto the chloride, and now we have 4 sets of dots and the -1 charge. Conjugate acid base is Bronsted-Lowry. Let's practice this a little further. This is you can tell this is a clip art from an old test question. What are the products of this acid-base mechanism? So the arrows are there. We have to figure out what's happening. First of all, whenever you see an alkaline metal, I don't care, sodium, lithium, potassium, just know that they're there as spectator ions. Because there is no such thing as just a negative, I do have to let you know that it has a first name. It does not play a role, so I can tell you automatically over here there'll still be a lithium ion floating around as a spectator. And when you see IPR, I want you to know that that's shorthand for the functional group called isopropyl. So if I were to draw N, and then you see IPR, it's isopropyl as the functional group. So just to give you a visual of what you're seeing here. Notice that it has a negative charge on it. And so what that means is that it's short some bonds. So nitrogen will have 3 bonds in a lone pair typically, but I only see 2 things attached to it. So that's kind of the structure of what we see here. N, IPR is isopropyl, and just visually you see that iso means that it's connecting to the second carbon of a propyl chain. Now let's come over here and take a look. I have a carbon, OCH, double bond O, I've got single bond, and this bond here is up to a hydrogen. Now thinking about the polarity and the electronegativity difference, we know that this carbon is being, the density is being pulled up to the oxygen, right? So this right here is a positive carbon, making this electron pull even more for the oxygen as it goes up. And so does this. The electron-rich area is up in this target. And because this hydrogen is next door to this carbon that's having its electron density pulled, you can see that this is going to be an electron deficient, partially positive area. Track the flow of the arrow. From the nitrogen, a set of electrons is going to form a bond to this hydrogen, and the hydrogen gets plucked off, right? That's what that arrow is representing. I am taking your hydrogen. So let's pause there for a moment. We've just figured out one of the products. The original nitrogen, who had isopropyl on it, that's just redrawing what's on the arrow. The arrow means added to as a reactant. And now all of a sudden you have an H plucked from the hydrocarbon chain. All right, so there you still have a lone pair there. One lone pair was used to form a bond. The second lone pair remains. There's the first product. Let's follow what's left of these arrows to figure out the remaining product. What does this other hydrocarbon remain? Well, I can still see like the backbone of the molecule. Just redraw. This had OCH3. I'm running out of room, so I'm going to just have to bring it down. And up here, we had a double bond. All right, so now let's track what happened. This bond is a set of electrons. It collapsed down. So instead of a single, we now have a double bond. This was a double, but one set collapsed back onto the oxygen, so now you're left with a single, and that's going to create a formal charge up there on the oxygen. We have 2 products that form. The hydrogen was plucked off of that hydrocarbon chain, creating the first product, a protonated version of N-IPR taken twice. Following the tracks of electron arrows that remained, this bond collapsed, so now I see a double. I drew that there. This double bond was broken, so the pi bond, the second bond, the pi bond became another set of electrons on the oxygen, giving it a -1 charge. Follow the electron arrows to predict the product. And you'll see then that this is conjugate acid-base chemistry. You end up here is a transfer of a proton. The base formed its conjugate acid. The acid formed its conjugate base. This is the Bronsted-Lowry acid-base theory. And if this were, in terms of being a multiple choice question, you still have to find the correct answer based on the multiple choice. So here I see how the answer was actually written. I see a protonated form of the original reactant. There's an H attached to the N. And I see that the double bond now has been moved and the negative charge up on the oxygen. So that's the visual of our representation of our final structures. Alrighty. This is an old test question as well. Again, tracking the flow of the electrons in this acid-base mechanism. Notice the nitrogen make excellent bases. There's a lone pair of electrons on a nitrogen. They're going to attach to a positively charged hydrogen. That's forming a bond. So one of ours has already been figured out. Remember, you see an Li, it's a spectator ion. So you'll know that that's just still floating on the product side. It was left unchanged. So there's the first product. It's a protonated form of the original amine group. Now track what's left. I have a benzene ring, so I might as well go ahead and draw that. That's not going to change. And then attached to it, we have an oxygen pointing up at that first carbon position. It had a double bond, but I see an electron flow that took the pi bond, that second in that double bond is a pi, and now created a single bond with an extra set of electrons and a formal charge of -1. This terminal carbon, which is here, and here, still has two H's on it. But instead of having this third hydrogen, these two electrons collapsed and made a double bond. So I'm following the electron arrows, predicting the product by just moving the electrons as shown in the arrows. And when I draw that in a multiple choice question, it simply becomes a matter of trying to find what choice matches yours. So here's your multiple choice. Which letter matches your drawing? Well, I can eliminate letter B because it's only showing one product. And I know Bronsted-Lowry transfers protons. We're going to have two products, a conjugate acid and a conjugate base. So just to remind ourselves, conjugates form. So this here was a base. It formed its conjugate acid. Therefore, this was the acid. It formed its conjugate base, which was one less proton. So as you're staring down your answers, which one matches? Which one matches those choices? Which ones can you eliminate? Which one matches? And pausing so that you can check that out. Let's focus more on Lewis acids and bases. I've kind of been dabbling with it. I want to formalize those definitions and practice these terms with you. Lewis acids are defined as electron pair acceptors. Lewis bases are electron pair donors. By far, this is a more important definition than Bronsted-Lowry, and it just seems to keep reappearing because we're really transferring electrons. Even if we're calling it Bronsted-Lowry, we're moving electrons with electron push arrows. So even though I can call this a Bronsted-Lowry base and I can call this a Bronsted-Lowry acid, let's open up the circle to this definition even more. An electron pair acceptor, an electron pair donor, as attaching new products and electron push arrows. So a base donates a pair of electrons. Whenever you see a nitrogen, it is a beautiful Lewis base because of the electron pair that sits open and ready to form an attachment to a new structure. And as I mentioned earlier, aluminum makes a beautiful Lewis acid because it has a valence that's deficient of an octet, so that aluminum is partially positive. And you can see that a new bond forms in an acid-base electron pair transfer. Lewis tracks electrons. Bronsted-Lowry transfers protons. So we just have a new definition in terms of acid-base chemistry. Instead of tracking H+, let's track what the electrons are doing and where they're moving from and where they're moving to. Let's model BF3 and NH3 and label. BF3, boron trifluoride. Boron lives in group 3A. It has 3 valence electrons. And when we draw its structure, it does not want an octet based on formal charge. So this is boron trifluoride. Notice that since boron has only 6 electrons, not 8, it makes a good target for a Lewis base. Let's draw ammonia. So here's nitrogen, and any amine derivative would have the same set of electrons on the top of the nitrogen. In the new theory called the Lewis acid-base theory, we start with electrons being transferred from an electron-rich to an electron-deficient site. Again, because boron is deficient, it's slightly positive, and we know that the arrows are kind of pulling out to make an electron-deficient boron. So what happens here? On the product side, instead of conjugates, because we're not transferring protons at all, we're forming an attachment. The boron trifluoride is now simply attached to the nitrogen from the original ammonia molecule. This is a new bond that forms. Notice that we made one product. There is no such thing as conjugate pairs in the from the Bronsted-Lowry theory. It's not brought forward to the Lewis theory. When we form a new bond, it's one product. This would be called a Lewis acid because it accepted an electron pair. This is called a Lewis base because it transferred an electron pair. A Lewis base, a Lewis acid, all about electron push arrows. Which of the following is a Lewis acid? So electron deficient. I want you to notice that hydronium H3O+ has an extra proton on it, doesn't it? And if you think about an electron, if it's going to be a Lewis acid, it's going to be a Bronsted-Lowry acid, it's going to be an Arrhenius acid. This extra proton makes a great ability to transfer, that electron set that's being transferred. So for instance, just a moment ago, we had NH3. This extra proton makes a great site of attachment to be attacked by an electron pair from a base. This makes an excellent acid. In Lewis theory, in Bronsted-Lowry theory, as well as the Arrhenius theory, it is an acid. The resulting formula would pull the proton and create the water. BF3, boron trifluoride. Again, notice that any group 3A makes an excellent acid because it's electron deficient. Boron trifluoride has no extra set of electrons on boron. It is trigonal planar, sp2 hybridized, just 3 domains. Therefore, it makes a great Lewis base because it has a site open for attachment to the boron. NF3. Now, nitrogen is always the base. It lives in group 5A. Oops, this is F. Group 5A says a lone pair of electrons, well, that's going to act as a base, not an acid. It's going to have the origin to go attach the boron or something. And, of course, OH negative is always a base as well. There's more than one answer. Both A and B are good Lewis acids. Which one is not a Lewis acid? All right, so this is kind of processing. Lewis acids, electron deficient. I know that group 3A make good acids because they're electron poor. They have only 3 domains, making them electron poor. So I know this aluminum bromide is an acid. I know it's a very good acid. That's supposed to be a C. Boron trichloride is also an acid. It's electron deficient. pH is the phenyl group. So here, and it's hooked to phosphorus. P lives in group 5A. So when I draw this particular structure, I'm drawing 3 benzene rings as the sites of attachments. And up here is a pair of electrons. Just like nitrogen is group 5A, underneath it is phosphorus, group 5A, lone sets of electrons. That's an excellent base. And what does D positive stand for? D is an isotope of hydrogen. It's called deuterium. Hydrogen comes in 3 flavors. You have protium, deuterium, and tritium. If you see D positive, it's just heavy hydrogen. Just transfer it in your mind to say H plus, hydrogen ion. It just has a neutron instead of it, making it a little heavier than the most common, which is protium. Protium, deuterium, tritium. Oops, that's a capital T. So D plus is a hydrogen ion that is not a good base. So the one that is not an acid, you're looking for a base. The only one here is letter C. Label each of the reactants. So I just want to know that I can see just one product, and one product tells me that it is not a Bronsted-Lowry, but it is a Lewis. Alrighty. Bronsted-Lowry requires conjugate pairs. There's no 2 sets of products over here, so I know that that's off the table. So I know it will be a Lewis acid and a Lewis base. Here is BF3. I know that that's a very electron deficient center in the boron. I know that because it's group 3A. And I need to remember group 3As like aluminum and boron are very good acids because they have a center that's positive. And you see over here in a very electron-rich area, this is going to be a Lewis base. What happens? These electrons attach to the central positive boron, and we see a new set of electrons bonding the 2 compounds together. So what used to be a set of lone pair has now become a bond between the 2 compounds, a single product in an electron transfer. Remember, the formal charge are shown as negative now on the boron and as positive on the oxygen. So that's what you're seeing there is a formal charge that develops from that electron transfer. I'm going to keep throwing just sample test questions, just sharing logic as we got a handle on our acid-base theories. So here's an old test question, and I see for an equilibrium, and I see reactants and products. First thing I notice is that there are 2 products. So on the right off the bat, I suspect Bronsted-Lowry and conjugate pairs. Because Lewis will form just 1 product, Bronsted-Lowry forms 2. Conjugate pairs differ by only 1 hydrogen ion. So I just like hooking together the conjugate pairs, those that differ by just 1 H. The one with more hydrogen is always the acid. The resulting species is its conjugate base. The one with less hydrogen is the base. The resulting species, after it accepted the proton, is called its conjugate acid. So which ones are acids? Well, it looks like CH3, NH3+, and hydronium, and that choice is letter D. Let's stop the video here and we'll pick up with new terms, carbocations and carboanions in our next lesson. Section 4 of our chapter, Heterolysis of bonds to carbon, resulting in a species known as carbocations and carbanions. This is a short section really to just introduce some vocabulary that we'll be carrying forward as we talk about more and more about reaction mechanisms. Heterolysis, hetero, more than one, right? So different throughout. Heterolytic bond cleavage. What I look at in this picture is that when I have a compound with a covalent bond, such as A attached to B, A is bonded to B by a set of shared pair, and I cleave that bond, which means break it. I'm going to break the bond, cleave the bond. If both electrons that are in the bond transfer to one of the two species, we have a heterolytic bond cleavage. Later, we'll introduce a homolytic bond cleavage in which one electron goes with each, forming a radical, but that is not the story in this chapter. So let's focus on both electrons going to the more electronegative species. So you see, if that happens, A results in a net positive charge, and B would result in a net negative charge. Suppose, just to put this in perspective, if HCl underwent a bond cleavage, heterolytic bond cleavage, and the shared pair of electrons in HCl, when this bond broke and both sets went to the chlorine, the more electronegative, you would end up with H+, no dots, and Cl negative with 8 dots. That's a heterolytic bond cleavage. In other words, both sets of shared pair go in one direction. Not one in each, but one paired share goes with just one of the two species. And it isn't going to happen just spontaneously. It has to happen with some sort of influence, some sort of assistance. This reminds me of like a single replacement reaction where the element called element Y is reacting with a compound called AB, element plus compound. Well, what happens if the element is strong enough, more electronegative enough, more active, it can displace the compound and steal its partner. And you'll see that B then is left alone as the new element, leaving you a new compound, YA. So the impetus here would be there has to be an influence to make this occur. If Y has a pair of electrons, it can abstract A and the electrons would collapse in on B, forming a new compound and element. When we see heterolysis resulting in a positive or negative charge on a carbon, we have some vocabulary words for it. Now let's think about what we have going on here. We have carbon, which has 4 bonds, so it has a completed octet. If the attachment to this functional group is more electronegative than the carbon itself, this could be an OH, it could be a halogen, it could be numerous things that are just more electronegative than the carbon. It results in a positive charge on the carbon and the electron density being pulled towards the more electronegative Z negative, whatever Z might be. If both of these electrons in that bond that cleaves collapse back onto the Z, those original electrons were still there, but both of them that were in the bond go with the Z as it leaves due to some persuasion in a reaction mechanism. When it takes the electrons, it results in a negative anion of Z. And since now carbon is electron deficient, only 3 sets of bonds instead of the 4, we see the positive charge resulting in a carbocation. When you see cation, we know that that means a positive ion. Suppose, and again, this was more polar, if the attachment, whatever the functional group might be, is less polar than the carbon itself, If it's less polar, when that bond is cleaved or broke, both electrons would then go back to the carbon, and if the carbon accepts them, notice now it's developed a formal charge of -1, and Z becomes a cation. This vocabulary word is called a carbanion. Carbanion means a negative ion. So predicting that which direction the electrons will flow is just understanding of electronegativity. And now that we see an electron-deficient carbon with a carbocation, an electron-rich area and a carbanion, we can apply those to our terms Lewis acid and Lewis base. Because carbocations that are electron-deficient, they have a positive center, well, they're going to act as Lewis acids. So in other words, there's a nice target there for a set of electrons from a Lewis base to form an attachment or a new bond. This is Lewis acid-base theory. And this is kind of a general formula, but if you look at a specific example, you see that water, for example, has two sets of electron pairs on that oxygen. Water is very electron-rich on the oxygen. And it can form, again, watch the arrow, it's going to attach to the carbon, which is electron deficient, and form a new bond between the carbon and the oxygen. In this example, the carbocation was a Lewis acid. A Lewis acid is electron deficient. Water acted as a Lewis base because it was electron rich, and we formed a new bond between the two. Carbocations are Lewis acids. Because carbocations are seeking electrons, we have a vocabulary word for them called electrophiles. When you see philes, it means loving. Electrophiles means electron loving. They are seeking electrons. Electrophiles are selected reagents that seek electrons to achieve a stable noble gas configuration. So if you see a carbocation that has this positive charge, it's electron deficient because it wants 4 bonds, currently only has 3. It's seeking electrons to stabilize its octet. Therefore, we call it an electrophile, electron seeking. It's positive. They're seeking electrons. All Lewis acids are electrophiles. By definition, if they're accepting electron pairs from a base, they're going to be seeking electrons. Carbocations, by definition, are electrophiles. All Lewis acids are electrophiles, and a negative anion would act as the base. So Lewis acids are electrophiles because they're seeking to fill its valent shell. They want to get rid of the positive and stabilize to have 4 bonds. Electrophile, seeking electrons. There are other electrophiles other than just positively charged ions, and that has to do with electronegativity differences between polar bonds. Remember this functional group called a carbonyl, C double bond O? The electronegativity difference between the carbon and the oxygen is significant enough that the positive charge falls on the carbon. It is not an ion because it still has 4 bonds, but the carbon itself is electron deficient based on the polarity of the bond. Based on the positive charge on the carbon, it will still seek electrons. It is still an electrophile, making a good target for a base to come form an attachment. Now remember, carbon still only wants 4 bonds, so we have to break the pi bond and let it collapse onto the oxygen to complete the oxygen 3 sets of electrons here. An electrophile is seeking negative charges from electrons, seeking electrons. They're positively charged areas. Could be a cation, but it could also just be positive area based on polarity. Okay, let's flip to the opposite of a cation. Let's talk about an anion. Carb anions are Lewis bases. Remember, to be a carb anion, you have an extra electron, right? So you have a negative charge on this particular carbon. So somehow this negative charge has been here because the electrons collapsed. Let's just redraw. If we had the structure Z, if you will, the electrons collapsed, giving carbon an electron-rich area with a negative charge. Well, if this is negative, it's going to be seeking a positive center. So therefore, its vocabulary word is called a nucleophile. Remember that the nucleus of an atom, the nucleus contains positive protons and neutral neutrons, but the nucleus is a positive center. And if the nucleus is positive, this electron-rich area is going to seek a positive charge. Nucleophile, positive loving. Think of it that way. Nucleus is positive, phile means loving. A nucleophile is seeking a positive region. Notice the abbreviation for nucleophile, NU, nucleophile. It will always show the electron set as a lone pair to remind you that it's carrying a negative charge. It's seeking the positive region from the electrophile. The nucleophile seeks the electrophile. Nucleophile has the negative charge. It is seeking positive. The electrophile has a positive charge. It is seeking electrons. The flow of electrons always originates from the nucleophile and goes to the electrophile. You can see that where the nucleophile, electron-rich, is seeking the positive of the electrophile, and you can see the new attachment and the bond collapsing on the oxygen, the pi bond. Here we see a carb-cation and a nucleophile. The carbocation is seeking electrons. The nucleophile is seeking the nucleus, positive protons. So we originate from the nucleophile to the electrophile. In this reaction, a clip art from a test question, which chemical species is acting as an electrophile? Which chemical species is seeking electrons? And to seek electrons, it's originally starting as a positive species. So I didn't include the A, B, C, D, E choices, but they're here, they're just pictures. So you really have two choices in this particular answer. Which species? So this is a species, and this is a species. Alrighty, so there's two choices. Which one is seeking electrons? Well, you can see right off the bat that the N double bond collapsed onto the nitrogen. Notice that this double bond is absent over here. Double bond is gone. And this, what was contained there is now attached to the oxygen. So the pi bond collapsed, and you see the +1 is now gone to no charge. So the electrons that were in this pi bond went to the nitrogen, and therefore you don't see a charge anymore on the product side. All right, so there's one flow of electrons. You see a second arrow originating from an electron-rich oxygen and pointing to, and it didn't land very well, but it's pointing to this carbon that's electron deficient. Now keep in mind polarity as well, and I keep erasing because I want to emphasize this carbon has its electron density being pulled significantly by the more electronegative element to nitrogen, making this a very positive center. So based on polarity difference in this bond, this carbon is an excellent target as a positive. It's positive, so it's seeking electrons. This is the species, that's the electrophile. This would be the species, that's the nucleophile. Let the arrows guide you. We can try this one as well. Identify the electrophile and the nucleophile, add curved arrows, and indicate the flow of electrons. Alrighty, so I just hand drew a test question. Sometimes it's easier to just hand draw them. All right, so we want to figure out electrophile and nucleophile. Right off the bat, the nucleophile by definition is seeking positive, so it's going to start negative. This is my nucleophile. Where is it being brought to? Well, here's a carbonyl, C double bond O. And remember we discussed carbonyl as a great target for nucleophiles because the carbon is left as a slightly positive charge based on the electronegativity difference. That carbon in a carbonyl is slightly positive, making a great target for the electrophile category. The curved arrow will originate at the lone set. Now notice where the target is. This is a carbon nitrogen. It's the carbon alone pair, not the N lone pair, that originates the arrow. If it were the lone pair on the nitrogen, the N would be up here, but it's not. So here's the origin, and that's the attack. The nucleophile seeks the electrophile. So I can see the attachment between the original carbon here, and there's the triple bond to nitrogen, and this original pi bond collapses back on the oxygen and made the single bond over here, resulting in the negative charge. Cyanide was the nucleophile. This aldehyde was the electrophile, and we drew two arrows to indicate the flow of electrons. When adding sodium azide, I'm going to just draw that. Sodium azide, NH2. Sodium is a spectator, Na plus, NH2 negative, sodium azide. To 2-butene, hear that, to 1-butene. The YNE ending lets me know that there is 4 carbons with a triple bond at position number 1, 1-butene. Here's a hydrogen, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3. So there's the structure for those particular compounds, the 2 reactants. All right, so I'm going to draw this H. Alrighty, so we have sodium azide. Sodium is a spectator, so Na plus, and then the azide part, NH2 negative. Clearly you see that this will be the nucleophile since it's a negative compound. It will be seeking positive charge. It is the Lewis base. Nucleophiles are Lewis bases. What we end up asking ourselves is, which one of these hydrogens will it attach? Which one is it going to reach over and take away? What you really want to know is, which hydrogen is the most positively charged? So we understand that electron density increases with multiple bonds. Between the 2 atoms, the triple bond has a much more greater electron density between those carbons than you would with the single bonds at the end of the hydrocarbon chain, making this particular hydrogen being pulled, that density being pulled away from it, making it very positive or easy to pluck off in this hydrocarbon chain. This is a much more acidic proton compared to the others in the less polar region. So down here we have less polarized bonds. C's and H are actually considered a nonpolar bond. But here, due to the triple bond density, this hydrogen has its electrons being pulled away, making it the better target. So that's the electrophile in that particular species. So what happens? Well, the N is going to extract that hydrogen. NH3 results. So we form a bond where one of the products is now ammonia, and the other product would still have C, triple bond C, single, single. But remember, this was now negative because you took away its hydrogen. So, of course, the sodium, which was its spectator, will be attracted now to that compound. So the sodium transfers. And which one of these matches that choice? Where you have the sodium attached to 1-butyne with the hydrogen abstracted, and the resulting proton transfer was ammonia. And you can see that my cursor highlighted that as NH3 with the sodium next to the carbon on the triple bond. The most acidic hydrogen was abstracted. So we can eliminate D and E because it didn't remove the correct hydrogen. I'm going to stop the lesson here. We'll pick up again with Ka and Kb talk and Bronsted-Lowry acids and bases. Let's continue our lessons in Organic Chemistry, Chapter 3, looking at Section 5 of our text, the strengths of acids and bases, from the Bronsted-Lowry theory, talking about Ka and the term pKa. So Bronsted-Lowry, turning our focus to conjugate pairs. So in contrast to strong acids, such as the 7 that we memorized, there were 7. Do you have them memorized yet? We had HCl, HBr, HI. And my pen got delayed. And we started that over. HBr, HI. Those were what we call binary acids. We moved to the oxy acids with chloric, perchloric, nitric, and then, of course, the diprotic sulfuric. These are the 7 strong acids that I want you to memorize. So when I say strong, they 100% dissociate, which means they do not set up an equilibrium. This focus of Section 5 are related to the weak acids, such as acetic acid, for example, where an equilibrium is set up. Notice the double arrow suggesting that reactants go to products in dynamic equilibrium with the reverse process of products forming back reactants. So let's take a peek just to remind ourselves about Ka, the acid dissociation constant, which brings back many lessons on equilibrium from Gen Chem 2, Chem 107 here at USM. Here we have acetic acid with a functional group COOH, the carbonyl C double bond O attached to the OH carboxylic acid functional group. We understand that the acidic proton is the one attached to the oxygen at the terminal end of the carbon chain. When it is placed into water, H2O, we see that a dynamic equilibrium sets up where we have a proton being transferred. Water is acting as a base, acetic acid as the Bronsted-Lowry acid. When it transfers a proton, acetate ion is the conjugate base that results, and the hydronium ion is the conjugate acid that's formed when the proton is accepted. If we take a 0.1 molar acetic acid solution, very common concentration in the lab, you can see only about 1% of the molecular form of the ion, over here is the molecular form, actually dissociates and forms its conjugate ions to the right. 99% of the equation lies to the left of our arrows. 1% lies to the right, the very definition of a weak acid. The equilibrium KEQ, the equilibrium constant, is the comparison of the products over reactants. So if we take a look at what this means, we have H3C, COO negative. That's this particular conjugate base written out in form CH3COO negative, its molar concentration units times the molar concentration of the hydronium ion, the second product, set over the original molecular form of the acid, CH3COOH, there's the COO, and the other reactant there, molecular form of water. The equilibrium expression, products over reactants, where the brackets stand for molar concentration units, moles per liter. So the value pointing to the right suggests there's not very many of the ion formed. Therefore, I would expect an equilibrium constant to be a very, very, very small number. When we look at the proton transfer between the carboxylic acid here, it's called acetic acid, organic name would be ethanoic acid, and the resulting conjugate pairs, we describe the KEQ, the equilibrium constant, which is just a number. The magnitude of the number indicates how strong the acid is. If you see an equilibrium constant that is a very large number, it indicates the forward reaction is being favored. And if you see a very small number, the reverse reaction is being favored. If we see the equilibrium constant where we have products over reactants, this is the definition of KEQ. Ka is derived from this definition. See where the water is on the bottom of the expression up above. If you were to take the KEQ, and just think about multiply H2O on both sides, you bring up that molar concentration of water, and we get an expression where we have the conjugate base called acetate times the conjugate acid called hydronium set over the original molecular form of acetic acid, or ethanoic acid, if you will. Bringing the water to the right side, we see this expression, and now we'll have our definition of Ka. So by definition, the equilibrium constant times the molarity of water gives us the derived value of Ka. Ka is called the acid dissociation constant. Ka is equivalent to saying the molarity of water, which is approximately 55.5 molar units when you think about a water molecule bombarding with a water molecule, forming hydronium and hydroxide. The molar concentration, if you derive 1 times 10 to the negative 14th, which is the Kw constant for water, and you can derive that value of 55 molar. So I won't go through that with you for now, but I'm just sharing where that comes from. It's a mathematical expression solved using Kw, letting X represent the ion concentrations. So KEQ times water is our definition of Ka. So again, KEQ is equal to, just thinking about that expression, if I want to isolate the equilibrium, it's Ka over the molar concentration of water, which has been determined to be about 55.5 molar units. I say this because sometimes I see test questions generate or populate in your multiple choice in Canvas, and it asks you to just reflect upon that very definition. So Ka is different than KEQ. KEQ is not the same as Ka, but it's a derivation from the equilibrium constant. How do we derive KEQ? And we can see just from the previous screen, it's the ratio of Ka over the concentration of water. To repeat ourselves, we derive that same expression right here. The equilibrium constant isolates Ka over H2O. And I just wanted to share that expression with you as if that question were to pop up in your test. So Ka is the acid dissociation constant. We had an entire chapter to Ka, Kw for acids and bases and their dissociations. We understand that Ka is a number. The bigger the number, the more the equilibrium lies to the right. And the smaller the number, the more the equilibrium lies to the left. So big numbers is a stronger acid. Smaller numbers means a weaker acid. The number itself has no units associated. It's the magnitude of the number that's interesting. It gives us an idea of the strength of the acid. And by strength, it's referring to how well does it dissociate when placed into water. Acidity and the pKa constant. Whenever you hear P, I want you to know that it's just a mathematical expression that stands for negative log. If we have pH, that means we take negative log of the acid ion. P represents negative log. POH literally means hit the negative log of the base ion concentration. P represents a mathematical expression of negative log. So if you see P, it means take the negative log of the Ka value and you'll get a pKa. And the reason we do that is just to have a number that's a little easier to handle than these very tiny numbers with scientific notation exponents. You'll see that we did the same reason for pH. Instead of handling numbers with scientific notation, we came up with a pH scale that ranges about 0 to 14. P stands for negative log. So just a moment ago, we mentioned that acetic acid has a Ka constant of 1.76 times 10 to the negative fifth. There's no units on a Ka. If you take the negative log of that value, you come up with 4.75. The pKa is negative log of Ka. And there's a practice in your sapling with just that simple math expression as well. If you're given the Ka values, how do you find or you're given the pKas, how do you find Ka? Just remind yourself, pKa is negative log of the Ka value. So therefore, Ka is 10 raised to the negative pKa constant. Just to help us remind ourselves, P, negative log, well, that's powers of 10. So as you work to solve these expressions, you're simply looking to put 10 raised to the negative pKa. So on your calculator, you would hit 10 raised to the, that's the caret key, negative 10.26. 10 raised to the negative 16.50. 10 raised to the negative 5.21. And hit equal, and you'll have a solution. Let me just model my calculator. I have it nearby. I'll model one of these three. I'm typing in 10. I hit the up caret key, and then negative 5.21 for the last example there. And my screen reads 6.165, so I'll keep 3 sig figs. 6.17 times 10 to the negative 6. No units on that value. If you have a pH of a 1 molar aqueous solution of ethanoic acid, there's the acid Q, given that its pKa value is 4.75. We need to calculate the pH. There are several review problems of equilibrium expressions that we were taught in Chem 107. To remind ourselves, our CH3, COOH, when placed into water, forms an equilibrium that highly favors the left side, where a proton transfers to create a conjugate base of the acid called acetate ion, and the conjugate acid of water, which would be hydronium. They're giving us a value of 4.75 as the pKa. The Ka is the expression of the concentration of the conjugate base, CH3COO negative, times the concentration of hydronium, H3O plus, set over the molecular concentration, CH3COOH. That's the expression known as Ka. Well, we were given pKa, so here I can write 10 to the negative 4.75. That's the Ka expression. Set equal to, well, what about these values for the ions? If we think about an old-fashioned ice chart, we would know that initially this was 1 molar, and initially these were 0. They had not yet formed in the initial concentration. I'll just write this ICE down here. So as time goes by, we see that the molecular form of the, I'll just write this out here. Just to remind ourselves what an ice chart looks like. Initially, we had 1 molar and no ions. As time goes by, we consume a value of X from the molecular form, and we produce the value of X of the ion form. At equilibrium, we would have 1 minus X, X, and X. Those are the values that we'll end up placing into our expression placed above. And remember, this is what ultimately we need for pH, is the molecular or the ion concentration of the acid ion, hydronium. So at equilibrium, we're letting X represent the concentration of CH3COO negative, the conjugate base, as well as the ion concentration of the hydronium ion, and 1 minus X represents the initial form of acetic acid. 10 raised to the negative 4.75 is our expression for Ka. It will be set equal to X squared over 1 minus X. We need to solve for X, where X represents the molar concentration of the hydronium ion, and from there we can find pH by taking the negative log of that acid ion. That's our solution pathway. I'm going to hit 10, caret key, raised to the negative 4.75 equals, and I have a value of 1.78 times 10 to the negative 5th equals X squared over 1 minus X. Let's bring that 1 minus X up to the left side. And now we're showing an algebraic expression where 1.78 needs to be distributed through 1 minus X. 1.78 times 10 to the negative 5th minus 1.78 times 10 to the negative 5th X equals X squared. We need to take this in terms of the quadratic equation formula, so we need an ABC value. I'm going to bring that X squared over and set it equal to 0, so that you now see that in terms of our quadratic equation, the letter A is equal to negative 1. The letter B is equal to negative 1.78 times 10 to the negative 5th. And the letter C is equal to positive 1.78 times 10 to the negative 5th. Use your quadratic formula on your calculator and solve for X. So on my programs, on my calculator, I hit program. Quad, C-U-A-D is the program. And for the number for A, I'm going to put -1. For the letter B, it's -1.78 to the -5th. And letter C is the positive of the same value. And X comes out to be 0.00421 for X. And I'll tell you, because the concentration of X is significantly small, you could have tossed out the -X and you'd still find the same answer, relatively the same. So back to the initial ice chart, we've decided it really was okay to toss out this X and just simply call it 1, and it would definitely simplify the math for you. So if you're not familiar with the quadratic formula, let the math become simplistic, where you would have just said 1.78 times 10 to the -5th is set equal to X squared over 1. That will toss out the -X because the insignificant number 0.00421 does not efficiently change the value of 1. It's called the 5% rule. If you square root, I'm going to hit square root 1.78 e -5, you will find that X equals 0.004219, essentially the same number. So just a little lesson, if you like the quadratic formula, I use the program, it's very simplistic. If you want to simplify the math, it would be fine as well. We still have to find the pH. So now that that's on my screen, I'll just go negative log that concentration, and we get a number 2.3747, 2.37. And coming back up to those multiple choice questions, 2.37, our answer would be 2.4 pH units. Ka is an expression that compares the concentration of the ions to the concentration of the molecular form of the acid, products over reactants. Let X represent the concentration of the ions set over 1. Ka was found by taking 10 raised to the negative pKa, and we solved for X. Once we had X, we used our pH formula. The pH formula pulled out the pH by taking negative log of the X. All kinds of review from a previous course. This is on page 114. I thought I'd give you one more practice problem with the mathematics, as it does appear in the multiple choice sections. We're given HCOOH, methanoic or formic acid. What are the molar concentrations of the two ions, called hydronium and formate, in a 0.1 molar aqueous solution? So thinking the Bronsted-Lowry conjugate pairs, we started with HCOOH, formic acid, the organic name of methanoic acid, since it's a carboxylic acid. When we look at the value of X at equilibrium and 0.1 for the value of the molecule, let's solve for the concentrations of the two acids. The Ka was given as 1.77 times 10 to the -4 units. The value of the two ions is both X, so I'll just place that as X squared over the original concentration of 0.1 molar, and I'm just going to toss out the X for the 5% rule. We want to solve for X. On my calculator, I'll hit 1.77 times 10 to the -4, so E -4, times 0.1. And now, of course, you see 1.77 times 10 to the -5th, and I need to square root that to isolate the X. Square root that answer, and you find 0.0042 molar units. Cross multiply, square root, and you find X. X represents the molar concentrations of each of the ions. What is the percent ionization? And to remind yourself, percent means part over whole. The concentration of the ion we determined above is 0.0042 molar units of the hydronium ion, the letter X, over the original concentration, which was 0.1 molar, expressed as a percentage. So taking that X value of 0.0042, dividing it 0.1, and expressing as a percent, you get 4.21% ionized, which allows us to say it was fine to toss out the X and not put 0.1 minus X, because the 5% rule says you can make the math simpler by tossing out the X if it's 5% ionized or less. Remember that acidity and pKa values. If the larger the Ka is the stronger acid, but by the time you take negative log, you want the smaller pKa to be the stronger acid. When you look, for example, of acetic acid, it's called ethanoic acid in organic chemistry. Of course, now I spelled it wrong. Sorry. ETH, ethane for 2 carbons, and the oic represents a carboxylic acid, ethanoic acid. This is the acid proton here in the Cu part of the molecule. We look up the pKa and it's 4.75. Let's remove these hydrogens and replace them with a much more electronegative element like fluorine. That creates the electron density being pulled away from that proton, and those fluorines are really hogging that electron density, pulling all the electron richness towards itself, leaving this proton very, very, very highly positive. As compared to these nonpolar bonds, the CH in this nonpolar region does not have that same pull in the direction, making this hydrogen less positive. More positive due to the electron distribution will create a stronger acid. This pKa is actually 0.18, where the pKa for acetic acid is 4.75. The stronger acid has a smaller pKa. The stronger acid would have a larger Ka, but take negative log, and it turns to a smaller number. Small numbers, strong acid, pKa chart. And that's really what you need to find for yourself in the test-taking tool page provided for you in our Canvas. It's table 3.1 on page 115 from your chemistry book. I'm using the 12th edition as stated in the syllabus. Print this and make it a test-taking tool page. On the very tippy top on the left-hand side, you'll see a list of acids starting from the strongest of strong acid at the top, going to the weakest of weak acids on the bottom. Notice on the right side, these are the conjugate bases. So here, these are the acids listed from strongest to weakest. And on this side, you'll see the conjugate bases, which means one less proton. The stronger the acid, the weaker the base. So the weak bases are at top, going to the stronger bases at the bottom. The stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. And so you see an increase from bottom to top. You're increasing strength of acid, but of course now you're increasing strength of base from top bottom. Just make sure you see this chart and spend some quality time with it. You'll be looking at it to find Kas. Again, just to repeat, table 3.1, page 115, you need a print. You can Google that pKa chart, or you can use the one that I've attached to our Canvas site and print that. Let's take a peek at some trends as we see and just kind of observations. A moment ago we said I had these hydrogens on the carbon and then a COOH. Here's the acid hydrogen. This was a nonpolar region. We replaced those hydrogens with fluorines, what happens to the acid, again, that acid hydrogen? What you want to notice is that based on the electronegativity pull away from these very, electronegative fluorines, this becomes a more positive hydrogen, which again we would know a nucleophile could easily pluck that hydrogen away in Lewis theory, making this a very attractive site, making it a stronger acid. Since this is a nonpolar region of the molecule, this is a less positive hydrogen. It's still acidic, but comparatively it's less acidic as compared to the fluorine induction. Okay, so just thinking about in the molecule, it matters what's attached to it to decide the strength of the acid and base. Let's compare the selection of acids and their conjugates. So here is an acid hydrogen highlighted in red throughout. All of these are acidic hydrogens. And when you remove the hydrogen, you get its conjugate base. So the difference between the top row of acid and the conjugate base. As we see, the more large the number is, okay, so kind of thinking about acid strength versus base strength. pKa values, we have -7 for HCl. That's a very strong acid. HCl is one of the 7 strong acids. HCl is listed as -7 on our pKa chart from table 3.1. Next, you see an OH from a carbonyl group. Here you have a protonated OH group, and here you have a hydronium ion followed by nitric acid. A very strong acid, HCl, produces a very weak base, Cl negative. If the acid is strong, it produces a weak conjugate base. The larger the pKa value for the acid, the stronger its conjugate base. The larger number means the least negative, if you will. So keeping in mind the trend, it's just kind of looking at the same chart from a moment ago, but in the opposite direction. So if I'm saying strong acid, you know its conjugate is weak. If I say weak acid, you know that its conjugate is strong. But instead of up and down arrows, we're now looking at these slides in terms of left and right arrows. Alrighty, so let's just try one out. I'm going to just backtrack. My slide went a little too fast there. Use your pKa table just to find methanol and water. And the question is, who is the stronger base? Stronger base. So when I think about finding the base, I'm going to just go ahead one, and this is a snapshot of that table 3.1. Just keep skimming. Do you see, and I've got all of this kind of pre-written, so let's bring our attention, and I'll write in green. To the previous slide, we were comparing methanol and water. And how did I know to go to the base side? Well, the question asked me who is the stronger conjugate base? Who's the stronger base? So I'm going to go to the right side of my pKa chart and find the two choices. Here's methanol and here's water. And remember, the stronger bases are below each other. So if I'm comparing methanol to water, water is the stronger base. It's as easy as just looking them up and finding the position on the chart. Methanol is the stronger base. Therefore, its conjugate acid, CH3OH2+, and the conjugate acid of water, H3O+, if this is the strong base, this is the weaker acid. Stronger base forms a weaker acid. Get familiar with the pKa chart and how to find them, and they go across by conjugate pairs. Here's water, its conjugate acid, H3O+. Here's methanol, its conjugate acid, CH3OH2+. Water was the stronger base. The protonated methanol is the stronger acid. I hope I said that right. Which of the following organic compounds has the strongest conjugate base? And they gave us the pKa values. So what I'm thinking about is how to best phrase this. If I want to know the strongest conjugate base, but they're giving me pKa's, not kB's, but Ka's, I want to flip this question around to say, all right, well, the strongest base means the weakest acid. And the weakest acids have the largest Ka values. So if I just talk myself through the strategy, the largest Ka, that's an easy question now, isn't it? Well, I don't even need my chart. If I just memorize the trend that Ka's, the P values, pKa, negative log of Ka, the weakest acids have the biggest number. So the strongest conjugate base has the weakest parent acid, and I just want to select the largest Ka. Which is the strongest acid? I don't know unless I use my Ka chart. But we can talk about a little bit of trends here. We can talk about things that we see in terms of numbers while we look at this particular problem. This is called ethanol. Its functional group is an alcohol. So we have an OH group. This is the protonized hydrogen. Ethanol is an alcohol. Letter B. See that Cu? That's an acetic acid. Its functional group is called a carboxylic acid, COOH. This is the acidic hydrogen. Here we have an ine, an ene, and an ane. Ethyne, ethene, ethane, going from triple bond, double bond, single bond. Now, this part was not provided in the question, but I took some time prior to the class and I wrote down the Ka values using my chart. I found ethanol, CH3, CH2OH. It has a value of 16. Can you point to that on your chart? Find it. It's kind of like 3/4 of the way down. 16 is its pKa. Carboxylic acid. Well, that's kind of a hint as soon as I say the word acid, which one's the strongest acid. Carboxylic acid, COOH. Cool. Find that number, 4.75. Put your finger on it. Do you see how it looks in your table 3.1? Ethyne, HC, triple bond CH. It has a number of 25. Find it on your chart and verify. You can read this. The ene ending is 44 and the ane ending is 50. Which one is the strongest acid? Well, of course, the strongest acid has the smallest number. The weakest acid has the largest number. So we can say this is the strongest and this is the weakest. And let's talk about why. And I want you to just think about structure as we talk about this. Here's CH3, CH2OH. That's structure 1. Structure 2, CH3, COOH. Here's triple bond, double bond, and a single bond. So these are the molecular structures of our 5 choices. An alcohol, carboxylic acid, ene, ine, ane. When I think about the strongest acid, you want to find who is the most positively charged proton. This hydrogen is indeed positively charged because the electronegativity difference between the O and the H creates a nice target to be, an electrophile. It's seeking electrons. It's a positive target. So it is a good acid. However, when I compare that to the C that's attached now to another oxygen, the electron is being pulled even further. The electron density is being pulled even further away from the acid proton, and I would say that this is even more positive. Again, the induction, the pull away from the hydrogen is caused to be greater because of the carbonyl functional group on the oxygen. Okay, so it's pulling it away further. Now, so that makes this more acidic. It's a stronger acid. Again, the reason, because of this other oxygen influencing the electron density around the hydrogen. There's more polarity surrounding that hydrogen, therefore it will be more positive. Let's find a trend here for the ine triple bond, ene double bond, and ane single bond. In other words, this is sp hybridization, this is sp2 hybridization, and this is sp3 hybridization. This hydrogen, and again it's symmetrical so I can point to either one, this hydrogen is left with a more positive partial charge because of the triple bond being pulled into the center of the carbons. The electron density is very, very concentrated between the two carbon atoms, and that hydrogen is a better positive charge. The electron distribution is away from it. When I look at hydrogens in a double bond, there is a greater density between the two carbons, but it's less positive from the triple. And by the time I get to all single bonds, the electron distribution between the two carbons is pretty even to where this is a non-polar molecule, and the hydrogen that would be, as a target would not be very acidic. It's not as positive. So I would say in a triple bond, this hydrogen is most positive. The hydrogen in a double bond is second most positive. And in the third bond, this single bond, this would be the least positively charged hydrogen. So although this is a nonpolar bond, it's a very, very, very poor acid because there's no unequal distribution of the charge at all. So a triple bond is more acidic than a double bond, which is more acidic than a single bond. And when you look at your pKa chart, if you just stare down that trend, notice that a triple bond, although it's close to the bottom, it is higher at pKa 25. The very last two in the left column, the ene is 44 and the ane, all saturated, is a 50. The trend shows that an sp triple bond is more acidic than an sp2 double bond, and the least acidic of all is the single bond sp3 hybridization. So even if we weren't provided a Ka chart, you could talk yourself through the order of those particular compounds, just thinking about electronegativity differences. Select the strongest base. Just check trends. You have hydroxide, you have a triple bond, an amide, a double bond, and a single bond. Who is the strongest base? Look on the left side of your pKa chart and you'll see the strongest base is the weakest, it's a conjugate base from the weakest acid. who is at the very, very, very bottom of the right side of your pKa chart? That's the strongest base. Well, the strongest base has a conjugate acid that we just talked about as being a very poor acid. Ethane, CH3CH3, a very poor acid, creates a very strong conjugate base. The correct sequence of ions shown in order of increasing basicity. Okay, so kind of think that through. Increasing basicity. That means you want to go to the right column, the conjugate base column, and order them from top to bottom as you find them on your pKa chart on the right side. See what an important test-taking tool page the pKa chart is. Alrighty. Now I want you to notice also that these are just the conjugates of an ane, ene, and yne. Every one of these is a triple, double, single. This is the yne, ene, ane ending. They're just rearranged in different order. Right? These are the conjugate bases of an alkyne, alkene, alkane. We want increasing basicity. So at the top, on the right side, the first one I see listed is HC, triple bond C, negative. It's just maybe, I don't know, 3/4 or 5/6 of the way down. You'll see that one written first. And then second from the bottom, I see H2C, double bond CH negative. And the very last one is CH3, single bond CH2 negative. The strongest is at the bottom on the base side. So now that you have them ordered correctly, how do you see that appear? Can you find the correct answer? Yne, then ene, then ane. And that's the order that you would list them. You'll have many practices like this. Rank the bold-faced hydrogens for the following, from most acidic to least acidic. Now this becomes a recognition of functional groups. In the functional groups, find the one that is highlighted. So this is the hydrogen. It's on a triple bond, so I wrote down structure 1 is an yne, alkyne. The YNE ending from my pKa chart I recorded for us as a 25. Here is a hydrogen in the functional group OH. The O is attached to 2 other carbons, so it is a secondary alcohol, a secondary positively charged alcohol. See how mandatory it is that you recognize functional groups to be able to find them on the pKa chart. Find on your pKa chart a positive secondary alcohol. And it may not be listed exactly, but you can sure find an about. CH3 taken twice, OH positive. Even though there's other things attached, that negative 3.8 on your pKa chart, please take a moment and find that so that you know how to work the pKa chart. You're finding a secondary positively charged alcohol. Here's the third structure. This is an H attached to a carbon that's in a double bond. So that's an ENE. I reported 44. Here's the the hydrogen attached in a functional group called a carboxylic acid, C double bond OOH. Carboxylic acid is that functional group, 4.75. And here in the last structure is the highlighted hydrogen, and that's a secondary amine, NH. The N is attached to 2 other R groups, making it a secondary amine. Take a moment and verify that with me, that you can find a secondary amine at around 36. The one in the book says isopropyl taken twice, NH, but that's for any secondary amine, so that's 36. The hardest part of this question was taking the time to recognize what functional group and looking at the pKa chart and writing them out. So now we want to rank them from the most acidic to the least acidic. Most acidic, lowest pKa value, structure 2. To the least acidic, which is the highest pKa value, structure 3. And just rank them from strongest to weakest using your Ka values. The importance of knowing your functional groups. Let's pause our lesson there and we'll pick up with section 6 when you're ready.